Okay, here's the last free response on the statics test. We have a beam on a hinge and it's supported by a cable, and we want to answer various questions about this system. And so the first question is, what is the tension in the cable? And so a free body diagram. We have forces here at the hinge that are unknown. You don't want to leave those out, but we can sum the torques about this point and they won't show up, at least in our calculation of the tension. We have the weight of the beam right at the middle, at the center of mass. And then we have the tension from the cable here, which I should label T. And then I have weight of this 50 kilogram mass pulling straight down. And so sum of the torques about the hinge equals 0. And I want the perpendicular component of the tension for its torque. And this is 70-degree angle here between the beam and the tension between the beam and the cable. You can show that. This is 50 degrees, this is 50 degrees. If this is 70 here, that's 20. And so this whole angle here is 70. And so tension times sine 70 times the lever arm. And then I have a negative torque from the two weights. And so it'd be 50. And then I need to figure out what this angle is to get the perpendicular component of the weight. And so if this is 50, this is 40 here. And so sine of 40 would be the opposite side, which is the perpendicular component, times the lever arm, and the other weight works the same way. So once you get sine 40 for one weight, you know it's sine 40 for the other, but it has a different lever arm and a different mass. And solve for tension, you get 435.7. And that's not easy to do. We're 3 points. I think you can see some erasers here, so I probably made a mistake somewhere. Looks like somewhere here, but I'm not sure. But I caught it. Now let's take a look at B. We're told that the rotational inertia of the strut about its center is 1/12 ml squared. And we want to show that the rotational inertia about its end is 1/3 ml squared. We did this several times in class, and it's the parallel axis theorem. And you had to show me you're using the parallel axis theorem. If you just kind of jumped in somewhere toward the end, you probably only got 1 point. And so show me what you're up to, parallel axis theorem. And so that means it's the rotational inertia about the center plus this correction term mh squared, where h is the distance from the rotation axis to the center of the object. And so since this thing has a length L, h is L over 2. So I get 1/12 ml squared plus m L over 2 squared. And so that gives me 1/4 ml squared for the correction term. So I get a common denominator multiplying by 3 over 3. So I've got 3/12, 1/12, that's 4/12, or 1/3 ml squared. And you should know how to do this for the AP test. There's a calculus way of doing this. You can look it up in chapter 11 of your book. But if you know this, you can use parallel axis theorem. It's way quicker. You get full credit, and you can figure out the rotational inertia about any point on a rod. And so this is a great thing to have in your calculator, so you can use parallel axis theorem to get the rotational inertia of a rod about any point. And we wanted to get that for the next parts because we're going to remove the 50 kilogram mass, so it is gone now. And we're cutting the cable, so there's no more tension. What is the initial angular acceleration? Angular acceleration is alpha. It is not omega. Don't confuse the two. Angular velocity is a different thing from angular acceleration. You need to know that. And so Newton's second law, sum of the torques equal I alpha. We already have the torque from the weight of the beam from above. And so you don't have to change anything here. I made it positive just so I get a positive answer, but it's okay to have it negative. And then I use the 1/3 ml squared that was given to me up here, whether I could prove it or not. That's what I need to use here. And solving for alpha, 0.94. And so that was worth 2 points. And then the strut is free to rotate in a complete circle. and so it's like sticking out from the surface here. Maybe this is a table or something, and so it can rotate all the way down to the lowest point here. And so how fast is it going? What's its angular velocity? And energy is the way to go because alpha is not constant up here. Notice it depends on the angle. And so alpha is not constant. I can't use rotational kinematics. And so I start with potential. It's the cable's cut when it's at rest. I end up with rotational kinetic. And so MGH is gravitational potential, 1/2 I omega squared, rotational kinetic, and set those equal. The mass cancels out. And kind of the key thing is what is the height? And so it's the center of mass change in height that you want. And so that's going to be, this is 5 and this is 50 degrees. And so this distance is 5 sine 50. So it falls to here, and then it falls another L over 2, or another 5. And so it's 5 plus, it's kind of going off the page there. So 5 sine 50 plus 5, or 8.83 is the total change in height. And then you get 2.28. People did pretty well in this. Not a lot of people switching these, which is pretty common. But if you're one of those people, make sure you understand the difference between these two. Angular acceleration is Newton's laws for rotation. Angular velocity, you want to use energy. Well, let's move on to the rotation test.